Hello everyone, welcome to the course Expansive Soil. Today's will be the 17th lecture and it will be module 6, and here we will learn about the behavior of expansive soil. Particularly in today's class, I will be discussing about the thermo-mechanical-hydraulic-chemical behavior of expansive soil. Before that, we need to understand how the soil behaves when we take a soil sample. The behavior of the soil will be governed by the two factors. One will be the net force, which will be like net force of attraction minus the repulsive force, and second one will be its fabrics. So, depending on the soil type or the clay type, the fabrics of the soil as well as the total net of attraction or repulsion will be different, and consequently the forces which governs this fabrics of the structure as well as the net repulsive and attractive forces will also change the behavior of the soil, and the factors which can control all this behavior also controls the total behavior of the soil sample. In the previous classes, we learned about three different minerals. One is the montmorillonite. We know that montmorillonite has a 2:1 structure, that is 2 silica sheets are present and a gibbsite sheet is sandwiched between the 2 silica sheets, and the distance between the 2 silica sheets is 9.6 angstrom in dry state, and in between these 2 sheets there will be exchangeable cations. These exchangeable cations can be sodium, potassium, magnesium, calcium, and depending on the type of exchangeable cations, the soil behavior will be different. These montmorillonite structures are very loosely bonded by weak van der Waals forces. Therefore, the water molecule can go inside. As the water molecules go inside this layer between this montmorillonite, there will be swelling of the soil, and when there is a swelling occurs, the distance between the layers will increase from 9.6 angstrom to a large value. Therefore, the montmorillonite will exhibit a higher swelling capacity in comparison to the other minerals. Talking about the different properties of the montmorillonite, the cation exchange capacity of montmorillonite is 80 to 150 milli equivalent per 100 gram, and it has a lateral dimension of 1000 to 5000 angstrom, and its thickness is about 10 to 50 angstrom. Since the particle size is very less for montmorillonite, it has a very large specific surface area. Due to its very large specific surface area, it can hold a large amount of water. Therefore, the swelling capacity of the soil will also be significantly higher. Depending on whether the most of the exchangeable cations are sodium or calcium, the behavior of the montmorillonite will be different. Say for example, the activity of sodium montmorillonite will be quite high, that is between 4 to 7 in comparison to a calcium montmorillonite, which will have a activity of around 1.5. Similarly, talking about the liquid limit of montmorillonite will be very high, and it can be up to 850 to 900%. Again, depending on the type of exchangeable cations present in the interlayer, the liquid limit can vary from 100 to 900%, whereas the plastic limit varies in a narrow range from 54 to 110%. Similarly, the shrinkage limit of montmorillonite is very less in comparison to other minerals, and it will be around 10 to 15%. Due to its high swelling capacity, the hydraulic conductivity of montmorillonite is very less, and it can be a value from 10 to the power minus 9 to 10 to the power minus 11 meter per second. Next will be the illite mineral. Illite mineral is also a 2:1 mineral, that is 2 silica sheets is present, and in between the 2 silica sheets 1 gibbsite sheet is present, and distance between the 2 layers is around 10 angstrom. But in between these 2 layers there will be potassium ion present. This potassium ion will fit perfectly into the hexagonal hole present in this silica sheets. So, therefore, this illite minerals is very less expanding in nature in comparison to montmorillonite. If we look into its properties, the cation exchange capacity of illite is 10 to 40 milli equivalent per 100 gram. The lateral dimension is 1000 to 5000 angstrom, and it has a thickness of 50 to 500 angstrom. And due to its little bit large size, the specific surface area is quite less in comparison to monochromolite, and it will be around 80 meter square per gram. In comparison to monochromolite, the activity of illite is quite less, and generally the activity will be in the range of 0.5 to 1.3. The liquid limit of illite is between 80 to 120%, the plastic limit is between 35 to 60%, and the shrinkage limit is bit higher in comparison to monochromolite, and it will be around 15 to 20%. Due to its less swelling tendency, the hydraulic conductivity of illite will be in the range of 10 to the power minus 8 to 10 to the power minus 9 meter per second. The third mineral which we discussed about in the earlier classes was the kaolinite. Kaolinite is a 1:1 mineral. We have one gibbsite and one silica sheets, and these are bonded by the strong hydrogen bonding. Because of this strong hydrogen bonding, generally these layers are inseparable. So, therefore, water will not be able to break into these layers, and therefore, the swelling capacity of kaolinite will be quite less in comparison to monochromolite or illite. The different properties of kaolinites are: the cation exchange capacity is very less, and it is in the range of 3 to 15 milli equivalent per 100 gram. The lateral dimension is 1000 to 20,000 angstrom, and the thickness is 100 to 1000 angstrom. And because of its large size, the specific surface area is very less in comparison to monochromolite and illite, and it is around 15 meters square per gram. Generally, the activity of kaolinite is very less and can be less active, and it is in the range of 0.3 to 0.5. The liquid limit of kaolinite is very less in comparison to monochromolite, and it will be in the range of 35 to 55%. The plastic limit is in between 25 to 40%. However, the shrinkage limit of kaolinite is quite high in comparison to monochromolite and illite, and it will be around 20 to 30%. Due to its less swelling tendency, the hydraulic conductivity of kaolinite is large in comparison to monochromolite and illite, and it will be in the range of 10 to the minus 7 to minus 9 meter per second. If we compare these three minerals together, we can see their sizes. The kaolinite will have the largest size among these three. So, here we can see the lateral dimension is quite large in comparison to illite and monochromolite, and similarly the thickness is also 10 to 20 times larger than the monochromolite. Due to this large size of these kaolinite particles, the specific surface area of kaolinite is very less. At the same time, the monochromolite will have the least particle size and the least thickness. Therefore, the total specific surface area of monochromolite will be quite high among these three minerals, and it will be in the range of 800 meter square per gram. Due to their large specific surface area and the cation exchange capacity and the presence of weak van der Waals forces, the monochromolite will have a tendency to swell. It has a tendency to absorb moisture, and therefore, it will have a tendency to swell to a large extent in comparison to kaolinite and illite. As I told you earlier, the behavior of the different minerals are governed by the two things or the two factors. These two factors are the net forces and its fabrics. So, when we compare these three minerals, generally the monochromolite is controlled by the net attractive forces, whereas the kaolinite is controlled by its fabrics. Therefore, when we compare the different properties of these two minerals, these two factors, that is the net attractive forces and the structure of the fabrics, will plays an important role in defining the behavior of these two minerals. So, we will look into all those behavior one by one, and also we will look how these two behaviors are differ from mineral to mineral, and what is the effect of chemicals and other factors on those behaviors. First, I will start with the liquid limit. As defined earlier, the liquid limit of a soil is defined as the minimum water content at which the soil starts to gain some shear strength, and depending on the type of mineral, the liquid limit will also be different. Mostly the liquid limit is controlled by the viscous diffuse double layer water. Higher is the diffuse double layer water, higher will be the liquid limit. Since the montomolinite is controlled by the diffuse double layer thickness, therefore, the liquid limit of montomolinite will also be controlled by the diffuse double layer thickness and the factors controlling the diffuse double layer thickness. Since the diffuse double layer thickness for montomolinite is quite large, therefore, the liquid limit of the montomolinite will also be quite large. At the same time, the diffuse double layer thickness will not develop for mineral kaolinite. Therefore, the mineral kaolinite will have low value of liquid limit in comparison to montomolinite or illite. And when we compare these three minerals, montomolinite will be having higher value of liquid limit in comparison to illite and kaolinite. And this higher value of liquid limit for montomolinite can be attributed because of its high specific surface area and large diffuse double layer thickness. As we know that there are different type of exchangeable cations present in between the montomolinite layers. Depending on what kind of exchangeable cations is dominant there, the liquid limit of montomolinite can be varied. If a large amount of sodium ion is present as an exchangeable cation, then in that case the liquid limit will be very high and it can be up to 800 to 900 percentage, and that montomolinite will be known as sodium montomolinite. If the exchangeable cation is dominant by calcium type, then the montomolinite will be known as calcium montomolinite, and it will have a smaller value of liquid limit and it can be in the range of 100 to 200 percentage. Due to this divalent nature, the force of attraction of the cations will be larger towards the clay surface, therefore, less amount of water can penetrate into interlayer. Therefore, the diffuse double layer thickness will be less for calcium montomolinite in comparison to the sodium montomolinite. Therefore, the sodium montomolinite will have a higher liquid limit in comparison to the calcium montomolinite. As the liquid limit of the soil will be controlled by the diffuse double layer thickness and which will be controlled by the type of exchangeable cation present. Here we can see a linear trend between the exchangeable sodium percentage and the liquid limit for montomolinite. Here we can see with increase in the sodium as an exchangeable cation, the liquid limit of montomolinite is increasing. So, amount of sodium ion present in the form of exchangeable cation can be expressed in terms of exchangeable sodium percentage, that is ESP, which is equals to the total amount of total sodium ion as an exchangeable cations divided by cation exchange capacity into 100. So, higher is the exchangeable sodium amount, higher will be the number of sodium ion in comparison to other ions, and therefore, the diffuse double layer thickness will be large and the liquid limit will be quite high. If we compare with the kaolinite, the diffuse double layer thickness will not be able to develop because the interlayers are strongly bonded by the hydrogen bonding. Therefore, we can see here the exchangeable sodium will have no relation with the liquid limit. Here we can see the exchangeable sodium has a quite good relation for montomolinite, but there is no relation exist between the liquid limit and exchangeable sodium percentage for kaolinite mineral. So, here we can conclude that the liquid limit of montomolinite depends on the diffuse double layer thickness whereas the liquid limit of kaolinite has no relation with the diffuse double layer thickness. And if we add different type of dielectric constant, as we know that diffuse double layer thickness is controlled by the dielectric constant, higher is the dielectric constant, higher will be the diffuse double layer thickness. So, for montomolnite, this is for montomolnite, we can see here with increase in the dielectric constant, the liquid limit of montomolnite soil is increasing. Here we need to understand the liquid limit of kaolinite is controlled by its fabrics. Mostly the kaolinite will exhibit a flocculated fabrics, and therefore, it can store a large amount of water in between their pore space. And as the dielectric constant of liquid will increase, the flocculated fabrics will also get disturbed. For example, when the dielectric constant is very less, say in this case, the net force for kaolinite will be attractive and the flocculated fabrics will be developed here, and as a result a large amount of void space between the flocculated particles will be there, and the water can be stored over here, water or fluid can be stored inside here, and therefore, the liquid limit will be very high. When we increase the dielectric constant, the net attractive forces will decrease, therefore, the flocculated fabrics will get disturbed and the liquid limit of the kaolinite will decrease. Therefore, we can see the two reverse trend for montomolnite and kaolinite, because the montomolnite's liquid limit is controlled by the diffuse double layer thickness, whereas the kaolinite liquid limit is controlled by its fabric. And with increase in the dielectric constant, the diffuse double layer thickness will increase, therefore, the liquid limit of montomolnite will increase. Similarly, for kaolinite, with decrease in the dielectric constant, the flocculated structure will be more, therefore, more water can be stored inside the pore space and the liquid limit will be more. So, therefore, lower is the dielectric constant, higher will be the liquid limit for the kaolinite. At the same time, lower will be the dielectric constant, lower will be the liquid limit for montomolnite. So, these two trends or these two reverse trend is generally due to this fabrics as well as the net attractive forces between the clay mineral. When we say about different type of exchangeable cations, here we can see the influence of different adsorbed cations on liquid and plastic limit of bentonite. Here we can see if the exchangeable cations is a lithium type, then the liquid limit will be 675 and the plastic limit will be 49.1 percentage. If we keep on increasing the size as well as the valency of the exchangeable cations, the liquid limit of montomolnite will keep on decreasing. Say for example, sodium which is a monovalent, calcium which is a divalent, if we compare their liquid limit, the liquid limit for sodium is 495, whereas for calcium it will be 125. And if we take the same valency, but larger the size of the adsorbed cation, we can see here sodium and ammonium. If we compare, sodium will have a smaller size in comparison to ammonium, therefore, the liquid limit for ammonium as an exchangeable cation will be less in comparison to the sodium. Therefore, we can say that the liquid limit will decrease with increase in the valency and it will decrease with increase in the size of the cation for the same valency. So, here we can see how the liquid limit and the plastic limit is changing for different type of adsorbed cation for a montomolnite mineral. Not only the type of exchangeable cations or the pore fluid chemistry, the amount of clay content or montomolnite content also controls the liquid limit. Say for example, if we take a soil sample and analyze the montomolinite content in it, we will find that with increase in the montomolinite content or bentonite content, the liquid limit of the soil will increase. In this plot we can see that with the increase in the bentonite content, bentonite is a soil which is mostly contains the montomolinite mineral. So, here we can see with increase in the bentonite content, the liquid limit will keep on increasing. So, these two trends has been developed for two different type of bentonite. One is a sodium type and another is a calcium type. So, depending on whether it is a sodium type or calcium type, the liquid limit of the two soils will be different for the same amount of bentonite content. If we take a bentonite content of 25%, say for example here, the soil consisting of bentonite of sodium type or montomolinite of sodium type will have a higher value of liquid limit in comparison to the montomolinite with a calcium type of exchangeable cations. Similarly, if we take another percentage over here, again the sodium montomolinite will give a higher value of liquid limit comparison to the calcium montomolinite. So, here also we can conclude with the increase in the bentonite content or montomolinite content in a soil, the liquid limit of the soil will increase. Next we will see what will be the effect of addition of salt on the liquid limit. As we know that the liquid limit of the soil is governed by the diffuse double layer thickness, particularly this for montomolinite type of mineral, the liquid limit will be controlled by the diffuse double layer thickness, and also the diffuse double layer thickness is controlled by or gets affected by the salt concentration and the valency of the salt. So, here we can see we have taken two different montomolinite, sodium montomolinite and calcium montomolinite, and it was exposed to two salts, sodium chloride and calcium chloride of different concentration. When we plot the liquid limit of these two montomolinite at different salt concentration, we can see that with increase in the salt concentration, the liquid limit of the soil is decreasing, and this decrease in the liquid limit is not uniform. For example, if we take sodium and calcium for the same concentration, the sodium will have a higher value of liquid limit in comparison to the calcium salt. Similarly, over here we can see the difference between the sodium chloride solution and calcium chloride solution for the same concentration. However, we can see here with the increase in the salt concentration, the difference between the liquid limit values for the two soils will be decreasing, and at higher concentration it will comes to an almost identical value. Not only the salt concentration and salt type, if we take different montomolinite, here we can see the effect of salt of different concentration and different valency will be different for the calcium montomolinite. If we compare for the same concentration, same salt for sodium montomolinite and calcium montomolinite, we can see here the calcium montomolinite will give a lower value of the liquid limit in comparison to the sodium montomolinite for any concentration. But at high concentration, the sodium montomolinite and calcium montomolinite will have a very almost identical value of the liquid limit. So, if we compare the total effect of salt on sodium and calcium montomolinite, the effect of salt on sodium montomolinite will be quite high, because the liquid limit of sodium montomolinite is changing from 600 to this value, whereas the calcium montomolinite it is changing from 220 to this value. Therefore, the effect of salt on sodium montomolinite will be quite high in comparison to the calcium montomolinite. So, here we can conclude that liquid limit of montomolinite decrease with the increase in the salt concentration due to a decrease in the diffuse double layer thickness. Now, if we can compare the liquid limit of montomolinite and kaolinite for two different concentration, here you can see for the same concentration, say for example 0.01 and sodium chloride solution, The monotomonite will have a liquid limit of 870 and kaolinite will have a liquid limit of 34. Now, if we increase the concentration from 0.01 N to 1 N, the liquid limit of sodium monotomolite will decrease to 350 percentage, whereas the kaolinite it will increase to 40 percentage. Now, these two trends are quite reverse. So, this is because of the factors which controlling the liquid limit behavior. Since it is controlled by the diffuse double layer, and as the diffuse double layer decreases with increase in the salt concentration, the liquid limit of monotomolite will decrease. For kaolinite, it is controlled by the fabrics. At high concentration, the soil or the mineral becomes more flocculated. Therefore, it will have a larger void space between its pores, and therefore, it can hold more amount of water, and that leads to a higher value of liquid limit in comparison to at less concentration. So, we can conclude here the liquid limit of kaolinite increases with increase in the salt concentration due to an increase in its flocculation behavior. As we increase the salt concentration, the net attractive forces will increase, and that leads to the flocculated structure of this kaolinite. Next, I will discuss about the shrinkage limit of the soil. The shrinkage limit is the minimum amount of water content up to which the soil remains saturated. If we take a soil sample and if we dry the soil, then the water content of the soil will be decreased, and so the volume of the soil will also decreased. This is a fully saturated soil. Now, as we decrease the water content, the volume of the soil will be decreasing, but after reaching a certain value of water content, the volume of the soil will not decrease. So, this is water and this is in the dry state. So, this is air in the dry state. So, volume is not decreasing after this point. So, this limiting water content after which the volume of the soil will not decrease is known as the shrinkage limit of the soil. The shrinkage limit of the soil is governed by its fabrics, whether it is a flocculated structure or dispersed structure. Generally, when we take a flocculated structure, say for example this one, we will have a large number of pore space or void space between them. Now, this void space hold more amount of water in comparison to a dispersed state. So, any soil which exhibit a flocculated structure can hold large amount of water, and if we dry the soil further, then the volume of the soil will not decrease beyond this volume. Therefore, the shrinkage limit will be higher for this soil. Hence, we can say that a soil exhibiting a flocculated structure will have a higher value of shrinkage limit in comparison to a soil exhibiting a dispersed structure. Here we can see a flocculated structure and a dispersed structure. So, soil structure and fabrics are most important parameters which controls the shrinkage behavior of the soil. Higher is the flocculated structure, higher is the amount of entrapped water will be present in the soil. When the soil dries, the water from this pore space gets emptied. Once the soil reaches to the shrinkage limit, a further reduction in the water will not change the volume. Therefore, higher is the amount of the flocculated structure, higher is the amount of water content it will have, and higher will be the shrinkage limit. Therefore, for a flocculated structure, due to the presence of the large size voids, the water content corresponding to the shrinkage limit will be higher. So, any clay mineral which exhibits a flocculated structure will have a higher value of shrinkage limit, and any mineral which will have the dispersed structure will have a lower value of shrinkage limit. We know that kaolinite exhibit a flocculated structure, therefore, kaolinite mineral will have a higher value of shrinkage limit in comparison to monotomolite, which will have a dispersed structure. So, therefore, the shrinkage limit of kaolinite is generally higher in comparison to montmolnite. Now, if we plot a graph between the shrinkage limit and the plasticity index, we can see that with increase in the plasticity index, the shrinkage limit is decreasing. So, this is because with increase in the plasticity index, the soil will have more dispersed structure, because with the increase in the plasticity index, the diffuse double layer thickness will also be large, and due to that the particles will be morely dispersed, and as the amount of dispersed structure will increase, the shrinkage limit will decrease. If we compare the shrinkage limit between montmolnite, halite and kaolinite, we can see montmolnite, since will have dispersed structure, it will have a least value of shrinkage limit in comparison to kaolinite because of its flocculated structure. And from this plot we can see higher is the diffuse double layer thickness, higher will be the dispersed structure, and lower will be the shrinkage limit. Therefore, a soil with a higher value of liquid limit will have a low value of shrinkage limit. Now, if we compare the shrinkage limit of montmolnite soil at different salt concentration and different type of valency of the salt, we can see this trend. As we know that with increase in the concentration, the diffuse double layer thickness will decrease, the repulsion between the particle will decrease, and the tendency towards the flocculation will increase. And as the tendency towards the flocculation will increase, the shrinkage limit will also increase. So, here we can see, say for example, for sodium chloride, if we plot the graph between the shrinkage limit and the salt concentration, with increase in the salt concentration, the shrinkage limit is keep on increasing. This is because with increase in the salt concentration, the diffuse double layer thickness will decrease. This leads to more flocculation, and more flocculation means higher will be the shrinkage limit. Similarly, for the same concentration, if we take the other cations of higher valency, with increase in the valency, again the diffuse double layer thickness will decrease. We know that diffuse double layer thickness is inversely proportional to the valency of the cation. Therefore, higher is the valency, lower will be the diffuse double layer thickness, more will be the flocculation, higher will be the shrinkage limit. So, here this trend also suggests that with increase in the salt concentration, the shrinkage limit will increase. With increase in the valency of this salt, the shrinkage limit will increase. So, therefore, we can conclude here the shrinkage limit is primarily governed by the clay fabrics, and shrinkage limit will increase with increase in the salt concentration due to an increase in the flocculation of the clay fabrics due to a decrease in the net repulsive forces because of decrease in the diffuse double layer thickness. Next, we will compare the activity of the soil. Activity generally is defined as the plasticity index divided by the clay fraction of the soil. Since the plasticity index is governed by the diffuse double layer thickness, the activity of the soil will also be controlled by the exchangeable sodium. So, here we can see, if we plot the graph between the activity and the exchangeable sodium percentage for two type of minerals, that is montmolnite and kaolinite, we can find a linear relationship between the activity and the exchangeable sodium percentage for montmolnite, because with increase in the exchangeable sodium percentage, the diffuse double layer thickness of montmolnite will increase, and this leads to a higher value of liquid limit and higher liquid limit means higher will be the plasticity index, and higher is the plasticity index means higher will be the activity. Since the kaolinite, it will not be governed by the diffusible layer thickness, therefore, we cannot find any correlation between the activity and the exchangeable sodium percentage for kaolinite, because the kaolinite will not be controlled by the diffusible layer thickness. So, therefore, there is no relationship between the activity and the exchangeable sodium percentage for kaolinite. Next, I will compare the swelling behavior of the soil. Swelling, we know that is a tendency of a soil to expand in its volume. This expansion takes place because of the movement of the water to the interlayer of the clay minerals. So, here you can see a montomonite mineral which have different exchangeable cations, and because of this concentration gradient here, the water can goes inside this interlayer. Therefore, there will be a swelling. As the water goes, the separation between these layers will increase, and that will be manifested as the increase in the volume of the soil sample. On the other hand, for kaolinite minerals, the silica and gibbsite sheets are strongly bonded by the hydrogen bonding. Therefore, water cannot penetrate into the interlayer of this silica and gibbsite sheets. Therefore, it will not expand when it will kept in contact with the water. Therefore, the swelling of kaolinite will be very less, whereas the swelling for montomonite will be very high. Now, we will see what are the different factors which controls the swelling behavior of these two minerals. Say for example, in here the different parameters which controls the swelling are taken. Say for example, in this case this is taken for montomonite. The effect of salt concentration has been taken here. We can see here this is the swollen volume of soil sample and different concentration, that is deionized water, that is 0N, 0.1 N of calcium chloride and 1 N of calcium chloride. We can see with increase in the salt concentration, the volume or the swelling volume of this montomonite is decreasing. Similarly, if we take the same concentration but different valency of these cations, we can see with increase in the valency of the cation, the swelling volume of the soil is decreasing. If we compare three different minerals and if we compare their swelling volume at water, we can see over here montomonite will have a highest value of swelling capacity in comparison to illite and kaolinite. Similarly, if we compare with the dielectric constant for montomonite, we can see here with increase in the dielectric constant, the swelling volume will increasing. Here the water which has a dielectric constant of 80 will give the highest value of swelling in comparison to the carbon tetrachloride which is a dielectric constant of 4. This increase in the swelling of montomonite is attributed due to the formation of the diffuse double layer. So, any factor which controls the diffuse double layer thickness will also control the swelling behavior of this montomonite. We know that the diffuse double layer thickness is controlled by the exchangeable sodium percentage. Higher is the exchangeable sodium percentage, higher will be the diffuse double layer thickness. So, if we plot a relationship between the swelling and the exchangeable sodium percentage for montomonite, we can see with increase in the exchangeable sodium percentage, the swelling of the soil is increasing. This increase in the swelling due to increase in the exchangeable sodium percentage is due to the higher value of the diffuse double layer thickness. Now, if we compare the effect of the pore fluid on bentonite it is an expansive soil which contains primarily the mineral montomonite, and black cotton soil is also another expansive soil which also contains the mineral montomonite, has been compared with kaolinite. Here the equilibrium sediment volume of the swollen soil sample has been taken for different dielectric constant. Earlier I have told that the montomonite is controlled by the diffuse double layer thickness, whereas the kaolinite is controlled by its fabrics, which is mostly flocculated fabric. Now, with increase in the dielectric constant, we know that diffuse double layer thickness will increase. The diffuse double layer thickness will have a direct correlation with the dielectric constant. As the diffuse double layer thickness will increase, the swelling volume of this montomonite soil will also increase. Similarly, the black cotton soil, which also contains the mineral montomonite, will also have a higher value of swelling when the dielectric constant will be higher. But a reverse trend can be seen for kaolinite. Kaolinite shows that with increase in the dielectric constant, the volume of the soil is decreasing, or at low dielectric constant, the kaolinite will have a very high value of swelling in comparison to a high dielectric constant. This is because of the fabrics, as I told you earlier. With decrease in the dielectric constant, the net force between the kaolinite mineral will be attractive, and therefore, they will form a flocculated structure. As the flocculated structure will have more volume, therefore, the volume of this kaolinite at low dielectric constant will be higher. As you increase the dielectric constant, the attractive forces will decrease, and that will also reduces the amount of flocculated structure in kaolinite, and that leads to a decrease in the volume of the kaolinite. If we compare with the different concentration of the sodium chloride solution with the equilibrium sediment volume of kaolinite, black cotton soil and bentonite, we can see over here, as we increase the concentration, the diffuse double layer thickness will decrease, and as the diffuse double layer thickness will decrease, the swollen volume of the soil will decrease. Similarly, for black cotton soil also, with increase in the concentration of the sodium chloride, the volume of the soil is decreasing. On the other hand, if we take the kaolinite, which is not governed by the diffuse double layer thickness or which will be governed by its fabric, has a reverse trend in comparison to montomonite or black cotton soil. With increase in the salt concentration, the volume equilibrium sediment volume of kaolinite will increase, because with increase in the salt concentration, the net attractive force between the particles will be more, and that will leads to higher value of flocculation and higher value of swelling in comparison to the less concentration. So, therefore, for kaolinite, with increase in the salt concentration, the volume of the soil will increase. So, here we can summarize that the swelling of bentonite is increased with the increase in the dielectric constant due to an increase in the diffuse double layer thickness. However, the swelling of kaolinite increases with a decrease in the dielectric constant due to increase in the flocculation tendency of kaolinite because of the increase in the net attractive forces. Here, effect of exchangeable cations present in the montomonite has been taken at various concentration to see the effect of type of exchangeable cations on the free swelling behavior at different concentration. So, two montomonite, sodium montomonite and calcium montomonite has been taken, and the free swelling was determined at different concentration of the salt solution. Two different salts of sodium chloride and calcium chloride was taken for this study. Here we can see for the sodium montomonite, with increase in the concentration, the swelling volume is decreasing. Similarly, with increase in the calcium chloride solution also, the swelling volume is decreasing. However, due to the change in the salt type from sodium to calcium, the swelling of the soil will be different. That means, the difference between the swelling for the same sodium montomonite will be different when we change from sodium to calcium, but at high concentration almost identical value of swelling can be observed. Now, if we compare with the calcium montomonite, for the same salt, same concentration, the sodium montomonite will have a higher value of swelling capacity in comparison to the calcium montomonite. This because of the divalence nature of this cation, which will be attracted very strongly to the clay particles in comparison to the sodium montomonite. Therefore, the swelling of the calcium montomonite will be less in comparison to the sodium montomonite for the same concentration, but at high concentration the difference between the salt concentration, the salt type and the bentonite or the montomonite type will be very less. The mostly all the difference can be observed to a higher extent for low salt concentration. Similarly, if we want to see the effect of the valence of the cation present in the pore fluid on the free swelling capacity, we can see here with increase in the valency of the cation of the pore fluid, the swelling of the soil is decreasing. This decrease is due to the decrease in the diffuse double layer thickness with the increase in the valency of the cation present in the pore fluid. So, here we can conclude the free swelling of montomonite decreases with increase in the salt concentration and valency of the cation of the pore fluid, and the effect of volume decrease due to increase in the salt concentration is more for sodium montomonite in comparison to the calcium montomonite. Next, I will discuss about the compaction characteristics of different minerals. We know that compaction is a process of densifying the soil by application of the mechanical energy, and in this process of compaction the soil grains are arranged in more densely fashion, and thereby the volume of the soil will gets decreased because of the expulsion of the air and the density will increase. Now, if we compare the compaction curve for kaolinite and montomonite, we will get two different curves. Here, if we see the compaction curve for montomonite and kaolinite, we can see that kaolinite will have a higher value of maximum dry density and lower value of optimum moisture content in comparison to montomonite. Here, this is the maximum dry density of montomonite and the OMC value of montomonite. So, this lower value of density of montomonite is because of the repulsion between the particles. With increase in the water content, the diffuse double layer will be developed in montomonite, and due to this the repulsion between the particles will increase. As the repulsion between the particles will increase, it will not allow the particles to come to a closer spacing. Therefore, the density of the montomonite soil will decrease. On the other hand, the diffuse double layer thickness for kaolinite will not be developed, and with the increase in the water content, the attractive forces for the kaolinite will increase, and it will lead to a more closely packing between the kaolinite particles. So, therefore, the density will be higher for kaolinite in comparison to the montomonite. Now, if we compare the different compaction energy with the maximum dry density, we can see that for the same compaction energy, kaolinite will have a higher value of dry density in comparison to the montomonite particles. Over here we can see. Similarly, here also if we compare the optimum moisture content with the compaction energy, we can see here that montomonite will have a higher value of optimum moisture content in comparison to kaolinite for the same compactive effort. This is for kaolinite, which have a lower value of optimum moisture content in comparison to the montomonite mineral. So, the montomonite exhibits a lower density in comparison to kaolinite due to the repulsion between the particles, which do not allow the particles to come to a closer spacing, therefore increasing the separation between the particles, which results in a decrease in the density of the montomonite soil. Now, if we compare the optimum moisture content with the liquid limit, we can see here with the increase in the liquid limit, the optimum moisture content is increasing. As we know that liquid limit of a soil is controlled by the diffuse stable layer thickness. Higher is the diffuse stable layer thickness, higher will be the repulsion between the particles. Therefore, lower will be the density and higher will be the optimum moisture content. Here also you can see the relationship between the maximum dry density and the liquid limit. As the increase in the liquid limit takes place, the maximum dry density of the soil will decrease. This is because again the diffuse stable layer thickness, as the diffuse stable layer thickness will be more, the repulsion between the particles will be more. As the repulsion between the particles will be more, it will not allow the particles to come to a closer spacing, therefore, the density of the soil will decrease. So, here we can conclude that optimum moisture content increases with increase in the liquid limit and maximum dry density will decrease with increase in the liquid limit of the montomonite soil. However, to increase the maximum dry density or decrease the optimum moisture content, we can add different non-expansive soil to montomonite. So, here we will see what is the effect of adding non-expansive soil to a montomonite and illite and their impact on the dry density and water content. Here 3 different soil samples were prepared by adding 50% of a non-expansive soil and 75% of non-expansive soil, and this is for a with pure expansive soil, that is sodium montomonite. That means, the sodium montomonite was added with 75% and 50% and then compaction was carried out. Here we can see this is for pure sodium montomonite, that is 100% montomonite. This is the montomonite content is 75% and here the montomonite content is 50%. With decrease in the montomonite content, the maximum dry density of the soil is increasing, and also with decrease in the montomonite content, the OMC of the soil is also decreasing. So, here we can see that for 50% of montomonite presence in the soil will have a lower value of optimum moisture content in comparison to this mixture containing 75% and 100% of sodium montomonite. And similarly, if we compare the maximum dry density, the soil containing less amount of montomonite will have a higher value of dry density. If we compare with the illite, the identical trend will be obtained. That means, with decrease in the illite contained in the mixture, the maximum dry density of the illitic soil will be increasing and the optimum moisture content of the soil will be decreasing. But if we compare the compaction curve for montomonite and illite, we can see that for 100% of sodium montomonite and 100% of illite, generally the illite will exhibit a lower value of optimum moisture content and higher value of maximum dry density in comparison to the sodium montomonite for the same compactive effort. Again, this is the higher value of maximum dry density and lower value of OMC for illite in comparison to sodium montomonite will be due to its lower value of diffuse stable layer thickness. Now, if we compare with the bentonite content or montomonite content with the dry density, we can see with increase in the montomonite content, the dry density of the soil will increase at the beginning and then it will starts to decrease. This first increase and then decrease in the dry density can be explained in terms of the soil fabrics over here. If we take a non-expansive soil like this one, this is a non-expansive solid particles, and if we filled with say montomonite particles, due to the small size of the montomonite particles, they will go into the inner void space between this large non-expansive soil particles. So, as we add or as we keep on increasing the montomonite content, this montomonite will starts to fill this void space. As the montomonite will starts to fill this void space, the density of the soil will be increasing. But once it fills this void space, a further addition of the montomonite will not increase the density, because once it starts to absorb the moisture, it will start to push these particles in upward direction. Therefore, the volume of the soil will starts to increase. As the volume of the soil starts to increase, the density of the soil will decrease. Therefore, initially with increase in the montomonite content or bentonite content, the dry density will increase, because at that time it will not be sufficient enough to fill this void space. Once the void space gets filled up, then a further addition of the bentonite content or montomonite content will not decrease the volume. In fact, it will increase the volume due to its swelling tendency. Therefore, the dry density of the soil will decrease. Now, if we compare the compaction curve at different salt concentration, we can see here these are the different compaction curve for different salt concentration, and this is with 0 deionized water, 0.01 N of concentration, 0.1 N of concentration and 1 N of concentration. So, as the concentration of the soil is increasing, the density of the soil will also increase, because the diffuse double layer thickness will decrease. As the diffuse double layer thickness will decrease, it will allow the particles to come to a closer spacing. Therefore, the dry density of the soil will be increasing, and the optimum moisture content of this soil will starts to decrease. Therefore, with increase in the salt concentration, the maximum dry density will be increased and the optimum moisture content will decrease. This can be attributed to a decrease in the diffuse double layer thickness, which allows the particles to come to a closer spacing. As the particle comes to a closer spacing, the density of the soil will be increased.